Right, so let's look at some reaction stoichiometry and what to do when you're working with reactions that take place in solutions. So now, most reactions that we look at in chemistry actually take place in solution. Um, and I mean, in fact, most reactions that take place in nature or any place that really take place in solution, meaning that in general, you will have two things that, or I say two things, or how many ever reagents that are in solution, and they each have their own concentrations, right? So a concentration A and a concentration B, and those react to give you some products. Okay, and we need to get used to working with concentrations and, of course, then subsequently the volumes of those species or the volumes of those solutions, and what happens when we add those together. How do we deal with those mechanics? Meaning, what will happen thereafter? All right, so that's the idea of this little short section. Um, And I mean, most of these will happen in water. So most of your solutions will be in water. And you need to be comfortable with the idea of concentration, so mole per liter molarity. All right. So just as we had earlier, where you must remind yourself that you cannot work directly in grams in any reaction, just as such, you cannot work directly with concentration. You must always work with the volume of solution, use the concentration, and work your way back to mole. So whenever you're doing any calculations with a chemical reaction, trying to determine limiting reagents or whatever, and you're given a concentration, you need to use the volume of that solution, its concentration, and work back to the mole of that reactant, relate it using the stoichiometric factors given in a chemical equation to another reactant, and then only you can look at the information given in the rest of your equation, or meaning whatever you're asked for about the products, or maybe about the different reactants, or what not. So the short example that I have here says metallic zinc reacts with aqueous hydrochloric acid as follows. So it says 1 mole of zinc reacts with 2 mole of hydrochloric acid to form zinc chloride in aqueous solution plus hydrogen gas. And then we're asked what volume of the hydrochloric acid solution, if it has a concentration of 2.5 molar in milliliter, is required to completely consume 1 or 11.8 gram of zinc. So we're given information about both the reactants, right? And we're told, right, we're given the mass of the zinc and we're given the concentration of the hydrochloric acid solution. And we're asked eventually what is the volume hydrochloric acid that we need to add in this situation to completely react with all of the zinc. So how would you approach this problem? Well, the only thing that you really can do is you first need to take this value to mole. Once you know the number of mole zinc, so mole zinc, once you know the number of mole zinc, we can determine the number of mole HCl, right? And once you have the number of mole of HCl, you can use its concentration. So that's mole per liter. So meaning you can divide by the concentration of the HCl, and that should then give you the volume HCl. So that's our roadmap, how to connect those quantities. And then, of course, we just need to remember to check whether or not it's in milliliter. Okay, so let's go ahead and do that. So our first step is we need to get mole zinc. So we take 11.8 gram, so 11.8 gram zinc, and we're going to divide by the molar mass, which is in this case 65.38 grams, so 1 mole of zinc weighs 65.38 gram. All right. And that should give you a value of 0.180 and so forth mole zinc. All right. Now we can use our chemical equations. All right. We know they react in a watt-to-watt ratio. So 1 mole of zinc reacts with 2 mole hydrochloric acid. At the moment, we have 0.180 mole zinc, and we want to determine with how many mole of hydrochloric acid does that react. So you can cross multiply, and essentially what you would get is that the number of mole of hydrochloric acid will be equal to 0.180 and so forth mole zinc multiplied by just your ratios. In other words, there's 2 mole HCl that reacts with 1 mole of zinc according to the reaction. So that means we require 0.360 mole, actually it's going to be 361, sorry, 361 and some numbers mole HCl. You see just roughly about that number there. All right, so now we have the mole hydrochloric acid. What do we also have? We're given the concentration HCl as 2.50 molar, and we recall that that means it's 2.50 mole per liter. Okay, so you can see, all right, if we take the inverse of that, so in other words, divide the number of mole of HCl by this concentration, we would get the quantity of liter. All right, so we can then say, right, volume HCl is going to be equal to the number of mole, which is 0.361, etc. mole HCl divided by the concentration, which is the same as saying there is 1.00 liter of solution, or in 1 liter there is 2.50 mole HCl, right? Because that is exactly what this equation tells us. For every 1 liter of solution, there is 2.5 mole of HCl. All right, it's a unit is a conversion factor that you know. All right, and that then gives us the value of 0.1444 liter. All right, of 2.50 molar HCl. Oops, that's not a capital letter, it's just a small letter. Right, and that's liter. But they asked for it in milliliter. So in other words, we just need to convert that quickly. So, I can do it. I like writing conversion factors. So, right, 0.144 liter. Remind yourself, what do we want? We want milliliter. What do we have? We have liter. And you can say, well, there is 10 to the negative 3 milliliter. No, sorry, there's 1,000 milliliter in 1 liter. Oopsie, that was almost a funny thing that happened there. There is 1000 milliliter in 1 liter, or there's 10 to the power minus 3 liter in a milliliter. All right, and that's then going to give you 144 milliliter. Okay, that's how much of the hydrochloric acid solution is required to fully react with the zinc. Okay, so I mean that's essentially it. Well, this is a very short example to just work with the ideas. But remember, so we first go to mole. From mole, then using the reaction equation, we get the number of mole of the other reactant. And then we use the concentration and the mole to get the volume. Okay, so that's typically how you would piece this together. All right. Thank you for watching as always, and I'll see you in the next video.